All right, good morning, everyone. I'm Mrinal Sood. I'm the Director of Technical Marketing at AEye, and today we're going to go over how we at AEye are improving perception through Lidar for situations when milliseconds count. Just a quick background about the company. Our founder, Louis Dusan, he built missile and plane tracking systems for the U.S. military. A lot of his inventions are commonly used in the battlefield today, and in 2013, he founded AEye to apply his learnings from the military background to the world of autonomous vehicles, especially for high-speed tracking. With that said, let's first go over how we drive. So our human mental processing time can be broken down into 4 typical sub-areas. During driving, you have sensation time that involves getting sensory inputs from things like brightness and contrast and size and loudness and so on. Recognition time is us making meaning of the sensation, like, okay, this shape is a tree or it's a person. And then we take the time to interpret the scene and possibly extrapolate into the future to try and become situationally aware of what's going on. So for example, if we see a pedestrian and look at our vehicle speed and the distance between us and the pedestrian, we could say, okay, whether or not we're going to collide with them or not. And then finally, we select a response and ask ourselves, okay, should I apply the brakes or should I just steer a little bit to the right? So that's our mental processing time. Once we select a response, we actually have to take time to move our hands for steering, as well as moving our feet laterally in order to press the pedals so we can engage the brake. And then after applying the brake, the stopping vehicle actually becomes the function of physical forces, and that includes gravity and friction. So things like condition of your brakes, tire pressure, road surface, asphalt, cement, gravel, all these things start coming into play in the vehicle response time. So this is a good visual to understand that stopping distance is actually the sum of both your reaction and braking distances. So if your reaction time is, let's say, 1 second, and you're traveling at 120 kilometers per hour, which means that you've traveled 33.3 meters in the time that it took for you to actually react. And then after that, the braking distance depends again on the vehicle condition and the driving location. So if we look at this chart, it shows you how the perception and reaction distances, they increase for cars and trucks based on speed. And for the general population to start gaining trust of autonomous vehicles, the machine perception and reaction distances have to surpass human perception and reaction distances. We're already at 150 meters on this chart at the max at the bottom for total stopping distance, and this chart is representative of favorable conditions. So I'm sure you all understand that once you go into inclement weather, adverse lighting, or lack of lighting, the perception, reaction, brake lag, braking distances will all start to get even longer than what's on the chart. So if we look at AVs, it turns out, AVs go through the same process that we go through. There's different types of sensing, perceiving, deciding, and acting. So we have sensors on the left, which have radars, cameras, lidars, and ultrasonic sensors. Then there's actually systems that make meaning of the sensory information through classification and tracking algorithms. And then they decide on a route and then make a trajectory. And then finally, they actually have to execute the driving maneuver. But for these systems to actually start coexisting with us on the interstates, they'll require high accuracy depth information at long distances, especially at high angular resolutions. This has been the missing link for high-speed autonomous vehicles because at speeds of 75 miles per hour or more, milliseconds matter, and these systems need obstacle avoidance capability beyond 150 meters and have inherent ability to track pedestrians, cyclists, and cars at 200 meters, both in daytime and at nighttime. So in order for me to talk about how we're enabling high-speed driving for AVs at AEye, let's take a quick look at how LiDAR perception works. Well, this is a very high-level overview, so we're going to do it in 8 steps. In the first step, you have scan definition and timing. This is where you're actually keeping track of the timestamp for each received point. So you get X, Y, and Z information and intensity information, but you have to keep track of when that information came in for each frame. Then you do some ground surface and curb estimation. So this is the first processing stage. You are separating the drivable areas from the non-traversable obstacles. So protruding and overhanging structures can be distinguished from the ground surface. So if things like overgrown tree branches or an overpass above you, you have to know what's the drivable surface from things above the vehicle. And then using algorithms like elevation mapping or horizontal slope detection, you actually start to do curb detection and know, okay, where's the exact road boundary? Then in step 3, you actually have to do some clustering. So using similarity criteria, you define whether some given points are belonging to the same physical object. And the most predominant criteria is the spatial measurements between, the spatial neighborhood between measurements, where you look at height similarities, vertical overlaps of neighboring points, and then you start to assign them to a cluster. In step 4, you do motion classification. So this is separating your movable from your stationary elements, and after you study a few frames of data. And in step 5, you extract features. So you're looking at the borders of the driving corridors, looking at elevated obstacles on and both next to the road. So the output of this step is knowing the overall free space, the lane markings, where the lanes are, what the lane width is, the obstacle types, and where the unknown regions are. And then you have to do some modeling. So by looking at the outer contour of a moving cluster and the vertical positions that are relative to the underlying ground surface, you want to distinguish between the corner and sides of a target. So you can start to say, okay, we're going to make sense of what that object may be and assign it to a class. And in this case, you're looking at the shape of that object or of that cluster, and you can say, okay, that is going to belong to the object class car. In step 7, you have to do some occlusion reasoning. So this is where you're considering the field of view limitations or objects that are farther ahead that could be occluded by objects that are closer. So in this case, you have a single-sided occlusion example, and you're going to experience this in adjacent lanes on the highways. And then on the right, you have a double-sided occlusion, which is commonly seen with cross traffic at intersections. And then in the final step, you have to track those objects. So based on the object type, the dimension, the velocity, you start to track them in real time before deciding what you're going to do in terms of steering, braking, or acceleration. So that 8-step process roughly sums up the high-level overview for LiDAR perception. Okay, now you understand how humans drive, you understand how important the stopping distance is, and now we just went over the 8 steps, so you have a general understanding of LiDAR perception. But as you can see, there's 3 ODD visuals here: parking lot, urban, and highway driving. And going back to my earlier point, when these systems start going at 75 miles per hour or more to coexist with us on the interstates, milliseconds matter, and the system must be able to plan the maneuvers, keeping in mind the total stopping distance based on the speed that the vehicle is operating at. So point density matters. In terms of LiDAR, the more points that are provided on an object or obstacle, the more reliable that whole 8-step process becomes. So range is extremely important, but it's useless without resolution to go along with it. So to feed the AV's perception systems, to feed them reliable, meaningful data with high confidence, we created our intelligent sensing platform that we call Foresight. It's a bistatic architecture, meaning that we have a separate transmit and receive path that don't actually depend on each other. So this allows us to have extreme configurability to independently optimize our laser firing, our beam steering, and our light receiving strategy, which allows us to program each shot. And there's going to be a video on this later. So our laser shot energy, our shot spacing, and shot rep rate are all configurable from frame to frame, and they can be changed for the ODD that you're going to drive in. And we enable our customers to make the most of this configurability by allowing them to actually trigger the different modes that they can configure based on the input from other sensors on the vehicle, including location, odometry, speed, or even your steering angle. So Foresight was also designed to allow optimizations over time over the air through software updates. So you might ask, okay, what is a performance mode? This is an easy way to visualize what a performance mode in our platform can look like. So if we look at the entire field of view, each dot represents a laser shot. And if you look at the different zones within the field of view, where we have different shot energies and shot spacing, that will impact our desired range and desired resolution. And by adjusting these parameters for ODDs, we can create a library of unique customer-centric performance modes that can be activated at any given time. So this way, we're always going to be providing meaningful information, again, for that 8-step process we went over earlier, whether it's an L2, L3, or L4 vehicle. So we take cues from the vehicle and change the performance to adapt to the different ODDs. But none of this would have been possible without our tiny beam steering device. So there's a laser, there's a beam steering device, and a receiver. And the extreme configurability is possible due to our MEMS device, which has a diameter roughly the size of the tip of a ballpoint pen. So with about 1 millimeter diameter, our MEMS allows us to scan extremely fast without enduring mechanical stresses so that we can change performance on the fly from frame to frame and adjust where our laser is going to fire. And again, because of the bistatic nature of the architecture, we're not transmitting and receiving from the same aperture, which a lot of our competitors have to do. And because that dependency limits your range and resolution, on the other hand, we can do what we call fire and forget. So we keep firing the laser without having to worry about light coming back from the same aperture. Most of our competitors, including those who use other larger MEMS devices, spinning polygons, galvos, and so on, typically have scanners that are larger than 3 millimeters. And these large steering devices experience larger amplitudes of acceleration under equal shock and vibration conditions. This is because we operate outside the range of automotive vibration frequencies, and that allows us to have inherent reliability and durability, not just for passenger cars, but also for commercial vehicles, which I think the previous talk highlighted as well. Here's a quick glance, and this is a photo, not a video, on the impact of performance modes. We'll have a video briefly. So again, if we revisit the 3 main operational domains, we have parking lot data on the left with a broad vertical field of view and information coming from, let's say, 125 meters. Then we have urban driving in the center with a dense region of interest at the horizon with information coming out to 200 meters. And then on the right, we have a highway driving example with a narrower vertical field of view and a highly dense ROI with information to track vehicles beyond 300 meters. So in parking lots, you care more about sudden appearances of shopping carts, people reversing out of spots, but you don't really care about what's happening 200 meters away. In urban driving, you're going faster and start to care more about intersections and bike lanes and cross traffic and so on. But on the highway, the impact, again, at 75 miles per hour can often be fatal. So detecting road debris, small obstacles like bricks or tires, these become extremely important. So you have to be able to have the obstacle detection capability at 150 meters or more, going back again to the total stopping distance chart. If a person happens to be on the highway because they pulled over, they got a flat tire, it's important to be able to detect them at 200 meters or more so the AV can plan a safe path for itself. And then finally, if we are tracking other motorists, including motorcycles, cars, trucks, it becomes critical that they have that capability out to 300 meters so that they have enough time to plan as well as stop the vehicle if needed, especially at highway speeds. So again, these capabilities are what will allow AVs to coexist with us on the interstates. So highly accurate point density at long ranges is what has been the missing link. So with all that said, in 2020, AEye and Continental, we have formed a symbiotic relationship We at AEye optimize performance modes and are responsible for the point cloud quality as well as making sure that the confidence fed into the perception systems is high. And Continental productizes and is responsible for the functional safety, validation, production, warranty, and support. And they also have sensor cleaning and defrost offerings for lidars based on, again, if you're mounted on the exterior of the vehicle. And together we're going to be launching the HRL product line in 2024. This is a good way to visualize how this relationship works. Together we engage customers, strategic customers, and tackle both the performance and product requirements for high-performance lidars for ADAS and AV markets globally. Customers will tell us what their deficits are for perception. Everybody uses different types of cameras, different types of radars, so no one has exactly the same type of requirement. So we sit down with them, they'll feed us their information of what they're looking for, we optimize modes that work for them, and then Continental finally delivers the product with the modes that we've created for that customer to the end customer. Okay, now let's watch a video that summarizes most of what I just said. I actually flew through a lot, and we're at 20 minutes, so we're good. Now the resolution and density at the bottom, we're not aiming at the sky, wasting energy. Here you're going to hear a tone every time. This is actually a real driving scenario, so every time we change a mode, there's an audible tone. You can see sort of the driving maneuver that's being performed with the icons on the bottom right. So that kind of summarizes the overall benefits for the Foresight platform, but I have one more video to drive the message home, and I'll leave you with this highway monitoring use case for ITS applications where we maintain pretty high point density on objects. You're going to see like 10-ish, 8 or 10 points out to 500 meters on cars, and this is possible because you're at a very high vantage point, so you're not being occluded by cars directly in front of you. There's no music on this one. You can see some of the cars there. It's what, 8 points. Okay, so yeah, when milliseconds matter, AEye's Foresight Intelligent Platform is there for the AVs. Thank you. Questions?
Okay. It's like I've done my steps for the month, by the way, in these 2 days.
Thanks for the presentation. I'm G from ZF. A quick question. How does the LiDAR know if there is a slope of the road so that you need to focus somewhat uphill?
So we don't actually keep track of the slope itself. We keep track of the 3D data, but the vehicle will provide odometry information and can trigger the sensor. So if there's an IMU in the vehicle and you're getting roll, pitch, and yaw information, you can use that information to tell the LiDAR if you want to go to a different mode that allows you to track the horizon of the vehicle or of the roadway.
The road can be flat, but there's maybe an upslope further away. So the LiDAR need to know aiming somewhat up when the vehicle is still on the flat sections. So how does that work to look at a further section of the road where is the uphill?
That's a good question. We do have in part of our, I guess, inherent firmware, we have the ability to do what we call pitch lock loop, where we kind of look at how the road gradient is changing, and then we adjust the ROI within the sensor. So there's two ways to do it. One is a hard-coded way where you're getting IMU information and telling it to go to certain modes. The other way is to use an inherent firmware feature where you're getting, you're using the sensor to actually detect the slope and move the horizon up or down.
Thanks.
Okay. Any more questions?
Thank you very much for the impressive presentation to us. I'm Michelle from RoboSense. I would like to know what kind of, LiDAR that AEye currently have at the moment for the mass production vehicles, and what the specs is like.
We could share this, you could reach out to us from our website to go over all the specs, but we have two ways that we tackle the different markets. In the automotive market, we actually don't sell direct. We license to tier 1 partners and launch partner is Continental. For that, the mass production sensor is going to be 2024. That's the HRL product that I showed. For the non-automotive market, for ITS, smart cities, securities, and all that, we have our own product, which we call Foresight M. I didn't show that here because we're not, this show is more about the AV and automotive market, but that product we actually are already in production.
All right. So the product that you are going to launch in 2024, is it solid state or the mechanical?
Yeah, I showed that MEMS module earlier. That's the beam steering device. It's a very tiny 1mm MEMS that we use for scanning.
Okay, thank you.
Thank you. Okay. No more questions? Sure? 100% sure? All right. Well, thank you very much. That was brilliant.
Thank you.